Today we're going to build something very 1970s-ish. We're going to build our own very bare bones rendering engine in SOPs. Now, why would you want to do this? Because in some cases, you might want a very quickish quote-unquote render engine that outputs your basic information passes like a normal map or a depth map in order to feed this into other algorithms. Let's call it that. And I'm foreshadowing a premium tutorial that we're going to release this week. So if you want to see what we're going to use this for, check back on Entagma on Thursday. And granted, I could use Houdini's built-in ROPs or a Solaris network, but I couldn't be bothered. And honestly, I personally also couldn't be bothered to set up this kind of rendering engine. So I did what I always do. I went for the lazy route and asked Chris. And thankfully, Chris clicked this thing together in like a minute or so, sent it over. And I think it's worth a walkthrough and worth mentioning how he built it and what he did. So let's start out in our Houdini session here by dropping down something that we want to render. And of course, Pighead is our prime suspect. Let's just dial in here and set it to, let's go with easy and add a subdivider. And maybe just an out null, so a null, which we're then gonna call out in all caps. All right, back up one level. And now let's add another GeoNode, call this renderer. And before we dive in here, let's add a camera to this viewport. So let's frame our pighead here and control click on the camera icon to place a camera in the viewport exactly where we were. In this case, I just want to unlock the camera from the viewport. So let's click the lock symbol here so I can move around in my viewport without moving the camera. However, in the camera itself, under the view tab, I want to change the resolution. In my case to a square aspect ratio, so let's go with 1024 by 1024 or 512 by 512. It doesn't really matter, as the resolution of our finally rendered out images will set in here in our renderer. We will do so by employing a grid, which will orient along the X and Y plane like so. Set its size to be 1 by 1. And then let's make sure that it fills the space between 0 and 1. And to do that, we'll have to move it along the X and the Y 0.5 units. So now this grid sits exactly in the space 0 to 1. Down here in the rows and columns is where we'll actually dial in the resolution of our final rendering. So in this case, let's go for 1024 by 1024. And as this should be square, let's just copy that parameter and down here paste that as a relative reference. So now we'll only have to dial in one parameter here. I am not really interested in the primitives here. I just need points. So let's use an add node to delete everything, but just keep the points here. And to make this a bit faster, let's for now go with 256 by 256 points, like so. All right, next we need a transform, which will wire into the side of this add here and move our grid back to -1 unit. So now it sits back here. And this particular position of the grid is crucial for the trick we're going to perform by dropping down a point VOP, one of the few instances where I think it's more comfortable to use a VOP over vex. And in here lives a magic node that allows you to transform this plane here into the camera space. What does that mean? So let's just drop down this node, which is called from NDC. And this as an input takes in the point position here. So every single point's position goes in here. And it also takes in a camera. In our case, we already linked to this camera here. And let's just straight up output this into our position. So now you can see this point grid fills exactly our whole viewport. So let's move to the side and we can see what happened here. This from NDC node moved the points exactly into the view frustum of our camera so that it fills the whole frame when we are looking through this camera here, like so. Now, let me look at this from the side again. So the crucial part here is this transformation. So we want this to be somewhere in front of the camera. So in our case, we just set it to -1. And it's also important that this is in the 00 to 11 space, as if it wouldn't be that, we can see this plane would not sit center in our viewing frustum. Also, now that this is linked to our camera, what this does is it also adapts to the camera's focal length. So with a longer focal length, this thing becomes smaller, and with a shorter focal length, this thing becomes wider to adapt to the camera's viewing frustum. Let's get back to our normal 50 millimeters here and back into our render SOPs here. The other thing that I need and I want for a rendering engine is some vector for each point that tells me in which direction I should shoot the rays, which I then will use to test intersection with my geometry. And we're going to write this information into the points normal, so let's display that. And there is none so far, so we need to create that. Let's do that in the point VOP as well. And I'll just copy this from NDC GeoNode. And instead of feeding it this grid, I will feed it a fixed position, a constant, which I'll set to be a vector like this, and then it should be all zeros that goes in here. So what this will do, it will create a positional vector at our origin of our scene and then transform this to the point where my camera sits, to the origin of the camera. And now that I have this grid and the origin of the camera, I can subtract the camera's origin from each point's position and thus generate a vector in which to shoot the rays. Let me demonstrate. I'm going to use a subtract node, and from our grid's positions, I'll subtract the camera origin's position, and then let's normalize this because, again, a normal should have a length of 1, so let's use a normalize node to make sure this vector is exactly 1 unit in length. And that goes into our normal slot. And now you can see I've got this pyramid of rays pointing in the direction of where I want to shoot my rays. Let's just go up to the OBJ context and pin our camera properties here and go back into the render. And now with our camera properties pinned, you can see that when I change the focal length, also the point positions and the size of the grid changes, but also the directions of the vectors. So that is working. Let's uncheck this here. And now the next thing I want to do, or I need to do, is checking where the rays I sent out from this grid into the scene intersect with some geometry. And the first thing to do is bring in the geometry I'm interested in here, in my case using an OBJ merge. And here I want to merge my pig head in the out. Now for later, I want this thing to have a bunch of attributes, the geometry. So let's just get rid of the normals here. Speaking of which, I need normals. So I'm going to use a normal node in here, just set to our defaults. Then for later, in some geometries, you want to render out a segmentation mask. So a different color for each connected geometry in this one here. And to do that later, let's use a connectivity node. Connectivity is set to primitive. And again, in the next step, let's attrib promote that back from primitive to a point. Let's change this thing to have a new name, and let's not delete the original. So the original is class. Let's call it segment on our points, like this. So now we do have a class attribute and a segment attribute on the points and the prims, basically storing the same data. Also, for good measure, if my object doesn't have any colors on it, let's just in here drop a color node. And you don't need that if your object coming in would already have point colors associated. So just this orangey color here. And that is my geometry I'm bringing in here. And again, creating a bunch of attributes just in case they should not be present on the geometry I'm bringing here anyways. Okay, this all goes into a point wrangle, which we're going to call intersect. And this is where we shoot the rays from our camera's grid up here, that's this thing, into the scene. So the grid goes into the first slot. We are interested in the grid's point colors in the end, because each of those points is a pixel in our final rendering. And then in the second input slot, we bring in our geometry. So to test for intersections in this scene, we're going to use a function called intersect. And this function, if it hits a geometry, stores the hit position as well as the UV coordinate at which it hit a geometry into two variables, which we'll have to create. Vectors. So we're going to create a variable, call it hit pos, and the other one, let's call it hit UVW. And in here, we're going to store the hit position and the hit UV coordinate using the intersect function, which is called like that. So we're going to create a variable, an integer variable called hit prim, and this will store the primitive number at which we hit a geometry. And then let's call the intersect function. And this takes in the geometry with which we want to intersect, which is coming in through the second input slot. That's the one with the number 1. Then we need to specify the origin from which we want to shoot the rays, in our case, each pixel's position here, so v at p, and then the direction in which we want to shoot those rays, which is our normal. Small caveat here, the length of the normal determines how far these rays will be shot into the scene, so let's add a good measure of wiggle room in here. And finally, we'll pass on the variables into which we'll store the hit position, and that should read hit position, not hit po, and the hit UVW, like so. Okay, that worked. So now we can check if our hit prim is actually 0 or larger than 0. So if our hit prim is larger than -1, then the first thing I want to do is set an attribute that stores a 1 if this pixel hit a geometry. And then I want to measure the distance from the hit point to the respective pixel on the grid here, which I can do by creating an attribute called depth. And let's just take the distance between the current point, that is pixel position, and the hit pos. So not much to see yet. So let's try visualizing this using a color node down here. And let's ramp from an attribute, in our case, the depth attribute. And you can see, well, this is all white. However, if we increase our maximum and minimum range, something like this, you can see we're getting a depth map here, especially if we look through our camera 1, you can see this overlay hiding the geometry behind that. We can even make that more pronounced by hitting D over the viewport, and in the geometry, let's just increase the point size here so you can see this is what we're rendering out, a depth map of our geometry. You've seen me already dial in this range from which distances we want to visualize this depth map. So let's automate this instead of me having to dial in the minimum and maximum depth always. And we're going to use the old trick here, just using an attrib promote, and in here we're going to change the new name, and we don't want to delete the original, with the original being called depth. And let's call this max depth. And let's set this to just promote the maximum number. And let's promote this to be a detail. So we're only promoting the maximum depth we found in here. And then let's use another point wrangle in which we'll feed this stream in here, which now contains the depth and the maximum depth attribute. So let's look up this maximum depth, which we just wrote into our detail attributes on our first input stream, one with the number 0, and we call it max depth. And then let's write this out into another attribute. Let's use a float attribute here and call it depth underscore normalized, or go with depth underscore norm for short, and should be equal to the value of our depth attribute, which should be fitted between 0, so that's the lowest value it can have when the geometry is directly intersecting our view plane here, and our maximum distance here, and we want to remap this between 1 if it's really close, and 0 if it's far away. So again, let's wire up a color node in here to visualize that, and let's ramp from the depth norm so we can see we now have this remap value, which makes it easy to read in the nearest and the farthest position in our rendered image. However, the background now is white, so let's fix that by using a point wrangle again, and let's call this one normalize depth, and this one fix unhit. And in here, in the fix unhit, we just want to select anything that is not in the hit group. And in our case, I will just set the normalized depth to 0. Let's move the color below here and see if that did anything. And it didn't, because we called this depth underscore norm. So like this, yeah, that works now. Now, in order to get this written out as a quote-unquote usable image within Houdini, I want to have this as a two-dimensional volume and not a grid of points. And in order to write this out into a volume, I want to use a trick. I want to use this original grid's position here and just copy over the attributes that I have here. And you could use either an attrib copy or, again, a point wrangle. In this case, we didn't change any point numbers, so we can just wire in the base grid here and the data grid, so to speak, here. And then let's, on our data grid, let's set the depth underscore norm to the value coming in through our second input slot that's stored on the points and is also called depth underscore norm. And we're going to use the points number as the points themselves didn't change, the geometry didn't change, so their point numbers didn't either. So let's wire up the color node here and visualize this, and we can see, yeah, that worked. To write this into a volume, what I want to do is create a volume first. Classic Houdini volume, and you can see this is offset to my grid here, so let's move that 0.5 units along the X and 0.5 along Y, like so. Also down here, let's make sure this is two-dimensional, and let's make sure this has the same sampling divisions as our grid by going to our grid, right-clicking in here, copy parameter, and then going back to our volume in here. Let's just paste this as a relative reference, and now we've got the same amount of voxels as we have as points. Finally, I can write this back into my grid. Down here, let's discard the color and use a volume from attribute node. Volume goes into the first, and then the attribute source, which is the points, goes in the second slot down here. And then in our volume from attribute, let's set the volume group, and let's call this volume that we just created here, let's call this thing depth, and it should be a scalar. So down here in the volume from attribute, let's set the depth using the depth norm attribute here. And now you can see our grid has transferred its values into this volume here. That's the basic setup. Now I want to add to this a few more volumes and a few more attributes. So instead of creating just a single volume here, let's just copy and paste this a few more times. And let's first create a vector volume. Let's call this thing norm for normal. And let's merge this with our other volume, so we can also feed it into our volume from attribute here, into the stream. And to get a shading normal or a hit normal from our geometry, what I want to do in our intersect node here, where I'm shooting out those rays, and looking where they intersect our scene after we hit something. I don't just want to calculate the distance from each point, but also I want to look up the normal on here on the geometry. And we can do that using a primuv function. So let's store a new vector, call this norm for normal, and it should be equal to the primuv, and primuv looks up an attribute on a certain point on the primitive and interpolates it as well. So for example, if you had just a plane here with 4 points and each point of the plane would store one end of the UV coordinates, no matter where you hit the plane, you would get the proper UV because it has been interpolated by this function here. This as an input takes again the geometry that we want to look this up from. So again, 1 for the second input slot. Then we want to look up the attribute that's called n with a capital N. So we want to look up this geometry's normal. And the primitive we want to look this up from is the hit primitive. And the UV coordinate we want to look this up is at the hit UVW coordinate, like so. Okay, let's just check. And in this case, I want to create a visualizer here. So right click into the visualizers and for the scene, add another visualizer, in this case, a color. And I want to visualize the attribute that is called norm. And you can see we are getting something here. However, if you have ever seen a normal map, you know that this does not look quite right yet. This looks a bit too overly saturated. And that is because now these pixel values are storing a normal vector. So a vector whose length is 1 at max, but that can also point into negative directions. So in here what happens is we are storing also negative values, which I don't want. So similarly to my normalized depth, which I do down here, let's drag this down and also add another point triangle and call this normalize normals, for lack of better words. So in our norm, what we want to do is we want to take our norm vector, the one we just wrote out and we are displaying here. And again, we want to fit its values. And again, as an input, we are taking the raw unfitted norm. And then we want to make sure to give it a min and a max of the input, and then a min and a max where it should reside afterwards. So afterwards, it should reside between 0, 0, 0 and 1, 1, 1 in RGB space. And before, it can reside in -1, -1, -1 to 1, 1, 1. So let's highlight that node. This looks much more like what you'd expect from a standard normal map. What else is there? Well, let's do a segmentation map as well. So in here, in the geometry that comes in here, we do have a segment attribute. So let's, to illustrate that, maybe go back to our test geometry down here and actually select a variant of the pig head that has different parts. So let's go with a hard pig head and let's uncheck add shader. And also for now, let's delete all the attributes on here and all the groups, just to prove that this works without any previous groups or any previous attributes. So also down here, we're going to delete all groups. So now we've only got positions coming out here. All right, back into our renderer. So in order to export a segmentation pass, what we want to do is look up an int. That is the class. I want to look this up from the current primitive we hit, which is coming in through a second input slot, again, ID1. Then we want to look up the class attribute, and the prim number is the hit prim. Again, in our visualizers, let's go in here, right click and edit this visualizer. And now let's visualize, let's call this thing segment. And the first thing we want to do is let's call this segment and just write out the class attribute directly. And you can see that is mostly black, a bit of red, and that's about it. Because when we look at the values of this class attribute, you can see that this is between 0 and 2. So instead, what I like to do is write this out as a vector and actually as a color vector and use the rand function to randomly assign one single color to one class, like so. And write this out as a vector like so. And now you can see we have these two, and let's look through the camera and maybe lock this to the viewport and move that around a bit. You can now see we have 3 different colors for each connected segment, the pig head and the 2 eyes. And actually this can go into one line like this, and let's delete that one. Yeah, that remains the same. One final thing I'd like from this 1970s render engine that we're building is a diffuse pass. And a diffuse pass that actually is independent of any lights that are in the scene. So we will build our own very amateurish shading model down here. And for that, let's have the user dial in a light direction and an ambient color. So let's add a vector, call this light dir, and give the user a vector input, which we'll call light direction. And also let's give the user the ability to dial in the ambient color again using a vector slider, this time called ambient_color. Let's create those sliders by clicking here, and down here let's dial in the light direction to be 1 along the y-axis and 0 along the other axes. For the ambient color, I'd rather like a color picker than these 3 values, so let's go up here to our cogwheel symbol, click Edit Parameter Interface, and then for our ambient color, let's set this type to be a color. Hit Apply and Accept, and now we should see a color field down here. So let's go for some bluish gray, like so. All right, got a light direction, got an ambient color. Let's quote unquote shade our geometry. So the first thing I want to do is read out any potential surface color at the hit point, which is written onto our geometry. Most likely that is a CD attribute. So let's look up the vector col, and again use the primuv function to maybe interpolate it. Coming in for a second slot, it's called CD, capital C, on our hit prim at our hit UVW position like this. Again, working in this node here. Next, let's calculate the actual shading. And we're going to use very simple shading here. We're just going to calculate the dot product between the light direction and the surface normal at the shading point. And the more both align, the brighter it'll be. So let's call this thing, I don't know, float amp. And let's calculate the dot product of the norm we just looked up. And maybe let's make sure that it's normalized. So if something has been messing up the normals, just make sure they have a length of 1. And then also let's normalize our light dir that we dialed in down here. And yeah, we called it light dir. Okay, semicolon. And that should be the amplitude. Now what I can do is take this color and multiply it by the amplitude. And then let's write it out. Vector at col equals to col. And let's see how that looks by again framing our grid here and going back to our intersect and maybe right clicking again in our viewport visualizers and then selecting the col. And yes, you can see we're getting a basic shading here. Again, let's look through the camera. Looks like this. And now what I want to do is bring in that ambient again. So to bring in the ambient, I could do different things. I could just add this and then remap this. In our case, why not blend it in just a bit? So let's interpolate between our current color and the ambient. And let's use a float slider again. Let's call this thing ambient strength to blend in the ambient. Let's create that slider, and down here, let's see what happens. So now, yeah, you can see we are blending in this ambient a bit to brighten up those dark-ish areas. Let's maybe desaturate this even more, a bit like that. I have another version of this ambient term that I'll provide in the scene file. It's a bit more complicated as it does some remapping of the colors. I think the output looks a tiny bit better, but it doesn't matter for the purpose that we are planning on using this. Just again, with all these attributes, for example, the normal, let's make sure we are also copying this over to our main grid that we then use to remap all those attributes into volumes. So let's just copy and paste this line, and let's bring over the normal. Let's pass one more, bring over the segment. And also, let's bring over the diffuse color. Like so. And of course, the color is a vector, as is the segment. Okay, let's add a bunch more volume from attributes by just copying, pasting this one. And we are just gonna cascade those. And we want to write the normal in this next vector. So down here, let's select the norm.star. And down here, let's write the normal into that. Let's just copy and paste this one more time, as well as this volume here. And down here, we're going to create this seg volume, which is also a vector volume. And down here, for the volume, we are selecting seg.star. And as an attribute, we're going to write the segment into it. And one final time, we are building the final piece of our cascade here by copying this node one more time, calling it col for color. And then down here, making sure we are importing col.star into col. Just like this. So now we've got a bunch of volumes. You see that for the vector volumes, the RGB volumes, we are having one single float volume for each channel. That's fine for now. Just to check this, what I want to do is drop down a COP2 network, which is Houdini's compositing network. So let's go into composite view. And in here, I want to use a SOP import to import the volumes that we created here. So maybe let's add a null and call this one out _ volumes. And then go back into our COPNet and in here select this certain SOP, and let's check resolution from SOP and set planes from SOP. So in here I can now view those individual planes, so the depth, the normal, which is weird and which I think we need to check, the segmentation that works, and the color that works as well. So let's check what went wrong with the normal. So up here I am creating the norm vector, which is an RGB. And down here, when I copied over this to the grid at the origin, I messed up the data type. This should be a vector, and let's see. Yep, that did it. Now, one thing that you can see, let's zoom in here, is this slight aliasing that you can see especially with the segment. So what we need to build is a cheap anti-aliasing. And the way we can do that is by just plainly and idiotically doubling this grid's resolution here. And then before we write this out into our COP2 network, just resize this thing using a volume resample and set its resolution to 0.5 to get back to the original size. And what we're now doing is exactly this. We are oversampling our volume, and let's just make sure we are importing this correctly. And now you can see we are getting this anti-aliasing, so looking a tiny bit better. All right, let's set my final resolution. Should be 512 by 512, as I need twice the resolution for the anti-aliasing. Let's set this to 1024 by 1024, and let's just go back to our COPNet, and in the COPNet, in the SOP import, let's click set resolution from SOP and set planes from SOP. And let's home this in. And this is our final quote unquote render. Now, why go through this hassle? Again, hinting at the next upcoming premium tutorial. What this does, although it's a bit of an effort building this, what this can do is, let me just create a new floating panel, which is pinned, and let's add a new pane tab, which should be a composite viewer. So in here, let's just pin this. We are viewing what we're seeing here in our composite viewer. And let's switch off the ACES and just switch this to raw. And maybe let's, I don't know, look at the normal and go back into our scene view. So also on our OBJ tab, we don't need the visibility of the render engine, as it doesn't matter to our COP network if it's visible or not. But if I look through this camera now, and again, let's lock it to the viewport and move this camera around, you can see that relatively quickly my COP network updates. And it'd update even quicker had I set the resolution lower or didn't oversample this. So instead of 1025 by 1025, sampling only 512 by 512 and not resizing this. And that allows us to reposition our viewport on the fly and our rendering, quote unquote rendering, being triggered immediately. So now that we built this, you can of course add to it. You could play around with it and add proper path tracing, for example, tracing GI through this, bouncing around multiple rays from each hit position. But I'm fine with those information passes here, giving me the depth, the normal, segmentation, and a really, really coarse diffuse color. And if you want to learn why this is enough for me to create a really nice image, you might want to consider becoming a patron of ours, as this is going to be our next premium tutorial. And generally, if you want to support us like what we're doing, consider becoming a patron of ours, as it is through the help of our patrons that we can run and tag the way we do. So thanks to everyone already supporting us, with a very special thank you going out to Blue Sky Studios, Man vs. Machine, Encore VFX, Supermassive Games, Important Looking Pirates, Jellyfish Pictures, The Mill, Method Studios, Via, NetherRealm, Gearbox Software, Electric Theater, Orkan, Parasol Island, Pixonic, Random42, Respawn, Rodeo Effects, Deviation Games, Tendril, Side Effects, Illusion, Nick, Rafik Anadol Studios, Rob Bryant Jr., Roger Letold, and Styleframe. Thanks so much for your support. And as always, until next time, it is cheers and goodbye.